Okay, so we're going to continue. So next, we'll discuss this Landau Ginzburg B model, a twist by a superpotential. Again, for Landau Ginzburg model, we have many different ways of describing this Landau Ginzburg model, from this Calabi-Yau geometry, from the categories, like categories of matrix factorizations or things like that. Again, it's along the same theme of this mini course. We're going to focus on the stream field description in terms of like Calabi-Yau geometry. So here's the basic setup. We consider Landau Ginzburg B model associated to the following data. So it's like a Calabi-Yau geometry, but now in this case, X usually is like a non-compact Calabi-Yau. Non-complex manifold. And secondly, omega again is like a holomorphic volume form on my space. So again, this is a Calabi-Yau form. And third, f is a holomorphic function on the space, which is called superpotential. This is called Landau Ginzburg superpotential. And such that the critical point of this function is compact. Okay, that's the basic setup. And it is at the third condition, this additional choice of this Landau Ginzburg superpotential holomorphic function, that we are forced to work on non-compact manifold. Otherwise, this function can only be constant function. Okay. And actually, in most examples, like you might have seen before, like this is like might be isolated critical point. But here we allow this one to be a little bit more general. It could be like a compact subset. Okay, so this is the basic data. Now, again, I mentioned like you can work with a categorical construction or geometric construction. We're going to focus on this geometric one. Now, the first one is like, because this is non-compact, then from a non-compact sense, like you might have some issues with, for example, doing integrations. You have to work with some object which decays fast, or something like that. So, for example, we're going to use a lot by comparison of these two objects. One of them is a compact supported polyvector field. Oh, by the way, so before we do this, let me introduce a few notations. So again, in this setup, we have the same object as before. So for example, we have this polyvector field. The same object, but now, because it's non-compact, to deal with some kind of integrations or some other constructions, we're going to work with, for example, sometimes we work with compactly supported subspace. So this is the subset of these polyvector fields which have complex support. And for this superpotential, we can basically twist the original complex a little bit by, for example, we're going to use like a twisted D-bar operator, which is given by d bar twist by acting on polyvector field is like a bracket with F. And you can somehow view this one as like contracting with the one form, df. Or if you turn this polyvector field to differential forms, literally this is given by wedge with df. But if you work with polyvector field, this is given by this bracket. And this one is also again the standard divergence operator with respect to the Calabi-Yau volume form. So this is going to be fixed again. And we have the same data, like we have, for example, if you work with compactly supported object, this complex, and this this divergence, this is a DG BV algebra, and this is subspace of the bigger one. This is all like DG BV algebra. So it's just to fix some notations. We're going to use this a lot. Okay. So first, let me mention that at the cohomology level, you don't lose much if you work with either model, like the full polyvector fields or this compactly supported object. The reason is pretty simple. It's like the lemma is like if you look at compactly supported polyvector fields, you look at this part, this d-bar operator, 2C d-bar operator. You look at this one as a subcomplex of the bigger one. This is actually is a quasi-isomorphism, which means that if you pass to cohomology, it's actually isomorphic. So the proof is just by this property, because the twist of this operation, if you look at this additional twist, it basically tells like away from the critical point, there's going to be Koszul complex, which is exact. So the only thing that can be non-trivial at the cohomology level will be supported around this complex supported locus. Then you can basically have the same data because now it's concentrated in this complex supported part. So it's a cyclic. Outside a small neighborhood. The critical point. Okay, so by this reason, sometimes when we pass to cohomology, we can use either one. But I will try to tell you like I will tell you like what's the difference, and actually this is not enough. We're gonna use something living in the middle, intermediate object. I will tell you the reason. Okay.
Can you twist by polyvector field?
Yeah, I can twist. Any solution for Morikawa equation, you can twist by that. Because this holomorphic function is a simple solution of Morikawa equation. Yes. Now, to apply Barannikov, Kontsevich construction, to obtain, like say, Frobenius manifold on this cohomology. We need to do a bunch of things. Let me try to explain. And this actually will have some trouble when we work with a little bit more general setting for this compact locus. But first of all, this is like this Frobenius manifold structure on this cohomology basically. But the bunch of things we need to do is like first one, we need a version of Hodge to drum degeneration. This is automatic when we work with like a compact Calabi-Yau, but it's not true in general for non-compact case. So we need some kind of E1 degeneration. of the spectral sequence for this t-adic filtration of the complex. For example, remember, like just do the same thing as what we call like S plus and S. For example, we have this. Squeeze too many E. Spectral. Yes, yes, okay. Yes, that's true. Sequence. Is this correct? It's the E1 degeneration, so it's not E2. If I write E2 degeneration, I'm going to write double E. Great. So, for this complex, like this same object as I called like S plus before on compact Calabi-Yau. And or if you want, you can work with like compact supported locus. And you might think like, which one is better? I will tell you like both are bad, but good in some sense, like bad in some sense. But anyway, this is a complex you can write down. And somehow you see like if you try to look at this complex, there's a filtration by the order of t. And you want this filtration by t degenerates at U1. So basically, the cohomology of this one leads to a basis for the full cohomology. So once you have that one, basically you can write the cohomology as the cohomology of this object, like joined with the parameter. And in this way, you just follow the same process as I explained for Calabi-Yau. You just complete the same process. You will discover that this object, just this object, is smooth formal in the sense of Barnikov-Kontsevich. So basically, this one says that has a universal period map, and if you look at the period map, you do this Berkeley factorization, you get this primitive form OJ function. Universal period map. And once using this period map, you can write down the Frobenius manifold. Okay, we'll come back to this degeneration soon, but that's actually one of the key issues here. The complex here is fixed omega, but the interpretation of this Mercalli equation by joining this parameter is like deforming the pair.
So it's just deforming E to the F times omega?
Yeah, it's like basically deforming this object. Yes.
For small t or for
T is like now at this point, when you deform this F by some parameter like universal unfolding and things like that. And that's why, for example, if you in the case of like isolated critical point, if you write down some universal unfolding, in this case degeneration follows automatically, and then you can write down find some particular sort unfolding which gives the primitive form. You can solve this quantum differential equation. And by just solving this Mercalli equation order by order. This is the algorithm that I designed with Chandon Lee and QD Saito. But that's a pretty like a formal step. Okay, that's the first thing. Second, we'll come back to that point. Second point is about trace pairing. On polyvector field. And remember, we have the trace pairing on Calabi-Yau in our previous compact Calabi-Yau models by just doing integration against the holomorphic volume form. And this one has to be compatible with the 2 differential in order to write down the higher residual pairing and this is symplectic form. So then we can write down something like omega is like trace pairing residue, something like that. Or if you don't take the residue, it's the higher residual pairing. Third.
So trace pairing is on compatible supported?
Yes, I mean this is only at this moment it's only well defined on compatible supported. So, but so it's of course isomorphic, and so it basically at the commodity level you can do either one. But you are right. There's indeed some issues. I come back to this soon. Basically, the 1 and 2 somehow they are not very compatible. Yeah, I will tell you what's happening. Then third one is like a compatible splitting. Basically, the the splitting of the Haught filtration. So basically, once you have one, assume we have one, and then you want to split in from this cohomology to this guy, which is compatible with the trace pairing or this high residual pairing. Which is compatible. and higher residue and higher residue. And such a choice, it was called by Kyoji Saito a notion of so-called good basis. And we have seen such object in the Calabi-Yau model as well. Okay.
So both of these, in the left hand side, right hand side, they depend only on the critical set, right? Is it independent of X or M?
It's going to be supported around this critical point, yes.
No, whether it will dependent on the minus one shift is structure.
Oh yes, that's true. Yes, only in the neighborhood. That's right. That's right. Yes, this is true. So the outside data is not important, but at some point, I'll tell you what's the data I need for something which. So if you are doing algebra, like algebra geometry, that's true. If you're doing differential geometry, that's not quite true, because somehow I need some control on the integration for this degeneration. So I need to do some kind of L2 analysis. And for this L2, I need some good behavior go beyond this critical point. So it decays a little bit faster in a way.
Yeah. Formal or something?
Oh, not quite formal. So I will tell you about it. So yeah, it depends on which category you work on. Okay, so by the way, just a remark. So what? Suppose this one has an isolated critical point. So this cohomology basically is supported at this point as given by this Milner ring. And yeah, if you work with -1 shifted, you can write down this complex, resolve this one in a different way, and this is one particular way to resolve this complex. But somehow, and in this case, this Hodge-Drum degeneration follows automatically. Simply because when you take the first cohomology, it's concentrated in just in only 1 degree, so nothing happens when you take the other differential.
What's the example which differs?
That's a good question. I don't know so far, actually. I can tell you what example they do hold. Yeah, I'm not sure, actually. That's a good point. Yeah, there are indeed some examples which doesn't hold in a lot, algebraically or geometrically, right? But I cannot, not in my mind at this moment. Okay, but anyway, so now let's try to describe this data. Okay, so first let me explain this trace pairing. So we can construct the trace pairing by exactly the same process as we did for Calabion. And so you basically do integration on compactly supported object. So for this one, this guy is more convenient. This model. So then we can define, for example, the same object, trace. The same formula. And with the same property as before, just let me list here. With, the proof is the same as well. Like if you could compute like a trace, so this school symmetric with respect to the twisted D-bar operator. And gradient symmetric with respect to the divergence operator. The same happens. Okay. And nothing strange at this moment. So also generalize the original construction, and you can write down the following pairing on at the bigger complex. So this trace pairing defines a pairing at the cohomology level. And first one is a trace, because it's compatible with twisted D-bar operator. Is a trace on this cohomology. And this is the analog of Poincare pairing. And secondly, the Chi-Restial pairing is the pairing on this S plus. Let me call this one QF. This is like this one is a sesquilinear pairing. Okay, so this QF is the d bar f plus td. And this is a linear in T and conjugate linear in the other on the other object. So it's like alpha ft. Yeah. That's the same formula. So, but let me just write it down because the same formula. SAT, yes. And you see, like the leading term, or the leading order of this pairing is given by the trace. Okay, so this this is called higher residual pairing. For the reason I'm explaining in a minute. So basically, in the case of isolated critical point, everything simplifies. So just remark. I assume with isolated critical point at the origin.
I'm sorry, there is only increased residue of Ft multiplied to minus.
No, just is valued in this range, in this space. Yeah. And if you work with Lorentz series in T and take the residue, and that's going to be the symplectic space, symplectic pairing on the full space. So here I only take the non-negative part. So I choose this omega to be like standard volume form, trivial volume form. Then I mentioned like this cohomology. This one is basically Jacobian ring. And this Jacobian ring can be identified as the same object by contracting with volume form. It's like holomorphic volume form quotient by like df. So this is like holomorphic volume form, like so n form quotient by this df, which holomorphic n minus 1 form. The same object and different way of presenting same object. Now this is a more geometric object, and on this one you get a pairing. Let's call this one omega f. Apply this construction to this setup. You got a pairing on this omega f. And you can show this is precisely the residual pairing.
So where did you use the function f rather than df?
What?
Most of the places you only use df.
Yeah, use df. You actually can work with a connection.
Yeah.
That's true. Yes. Yeah. And I think we are working on that somewhere. Yeah, that's true. Yeah. And you indicate the zero locus of the connection, and you can do more geometric setting global works. Yes. Then this precise the residual pairing. Like if you try to take the trace pairing of this alpha z as holomorphic object or algebraic object, literally you find standard algebraic geometric object like residue, like alpha, beta, and partial 1. Literally this formula, this trace formula, just pairing, is precisely the residue pairing. Yeah. So you can find this calculation in my work with Chandran Lee and Kyoji Saito, where once you observe this, then you basically go to this step to obtain this higher residual pairing is automatic. Okay. So in particular, this KF, if you apply to, like say, in this setup, like apply to alpha z, beta z, these two objects, holomorph functions. Actually, in this notation, I really mean some object in this polyvector field, so that's why I write just alpha beta. Now, you take the pairing, and you see like the leading term is given by this residue. Let's call this one K0, K1, and essential. So this is residue. Literally, this residue I just mentioned, this trace pairing, and all the other terms, all the other constructions are called higher residue pairings. And that explains the name. This is the one by QG Saito. Okay. Now, that's for the pairing. Now let me go back to discuss the degeneration issue.
So alpha is alpha zt. Alpha depending on T.
Well, yes. Then you have other terms. So here is really no T here. Just really holomorph functions. You represent holomorph function as an element in this cohomology. Yeah. But if you had T, then you have like this linear in T here and sesquilinear in T here. So, well, literally, if you just write down holomorph function, that is the data, and view this holomorph function as an cohomology class here. Or let me say cohomology class in this. Oh, it's the same thing as this cohomology. Sorry, you view this holomorph function as a cohomology here, and then you do this calculation in this competitive supported cohomology, and then you calculate this pairing. That is literally residue and higher residue in sexual. So this is the same thing as this cohomology. Isomorphic. So throw into two holomorph functions, view them here, and identify them as an element here. So you need to do some kind of transfer. Not transfer, just like to do some kind of chain homotopy, and then calculate the residue here. And we showed this is basically the same as higher residue pairing.
So this is
Double bracket T.
you write this last.
This one? Yeah, that's right. You're right. Thank you. Yeah, this is isomorphic. So holomorph functions is a natural map into this space.
I'm saying if you write alpha z, is alpha z in the one with no T, the PC,
No.
the T outside?
Alpha z. So holomorph functions mapped here.
Well, alpha z is just a holomorphic
Yeah.
function. It's not a class in general. This is just a
Holomorph function.
function.
Yeah. It's really literally holomorph function. Yeah. Okay.
This but you do not use no splitting is used.
No, yeah, not yet. So I'm coming to this. It's a very class. So this is like half of the geometry. You want to do the other half. Yeah. So this Hodge to the round. Let me explain the issue first. First, you know this guy, this object. Oh, it's actually somehow good because this model's algebraic object. So it's a resolution of the holomorph functions, or if you want, you can work with holomorphic object, or algebraic object. So this is good for many other reasons, but somehow bad for integration. So this is too big. for trace. Basically, because my X is non-compact, so it just cannot integrate this object directly. That's why in this is sort of amusing. Like, if you want to calculate the trace of these holomorph functions, and you do this kind of identification and make it compact supported, and then do it. So it's really a cohomology construction, but at channel level, this doesn't work directly. So instead, I used this compact supported polyvector field, which behaves better for integration, but this one is bad for Hodge decomposition. It's too small. Like in the compact Calabi-Yau case, we don't have this issue. Like we have this, we have nice operators like d bar and d. We can do this Hodge decomposition directly. But here, if you work with compact supported object and then you do like Hodge decomposition for d bar, and this harmonics, for example, will lie outside of this data, so it doesn't. It's not preserved on the Hodge decomposition. Now you can work something other, like for example L2 aspect sections of this polyvector field. This is good for integration, for example, pairing, and also good for Hodge decomposition. We know this can be this is basically designed for this harmonic analysis, but somehow this one is bad for nonlinear object. For example, like a product, or any, because, for example, this is really a DGLA. We want to make a product, and when we write down, for example, write action functionals, we make a bunch of objects and multiply them together and want to integrate. All this kind of nonlinear structure somehow doesn't work in general for all L2 sections, so you have to be a little bit more careful. So each model has its good things and bad things. So now I will introduce another model which can be used to solve all these three issues automatically. So this is a good thing that I want to explain. So let me, okay. So let's introduce the intermediate object. And this is introduced with the Wen Hao in our work. I will try to explain this. So it's going to be something sitting in the between, like compact supported. I'm going to call this one poly F infinity. We call this one F adapted polyvector field, but it's basically a twisted version of this subloop spaces. So such that this object enjoy all three properties. So first, integration. Second, Hodge decomposition. Third, all natural nonlinear product. This is a nonlinear object structure, like the product. So let me try to explain this. So by definition, I mean, this guy equals, roughly speaking, a twisted version of this subloop spaces. is given by all those elements in L2 sections of this polyvector field, more precise. And to define the Sobolev norms, we have to take, for example, all derivatives of this guy and make sure like this still lies in L2. In the twisted case, we add something more. So we require all this kind of a twisted norms. Like, for example, if you take derivatives, some derivatives of this polyvector field, and then you multiply by all powers of this derivative for the superpotential, and you require all this kind of object lies in L2. That's the definition. So, and with this definition, I'll tell you something good about this notion. So I need another notion which we call this bounded Calabi-Yau geometry. So let me be a little bit brief here. So now we're going to choose a metric, Kähler metric, G. And this is my Calabi-Yau volume form. This one will be called a bounded Calabi-Yau geometry. If the metric, this metric has to be complete, and this is the pair of metric, and this one has to be bounded geometry. So if this object is bounded geometry, this means that this is a complete Riemannian space. And for example, you look at all these derivatives of the curvature, they are bounded. And this one also has a positive injective radius. So that's somehow, if you take the derivatives, all these metric and curvatures, they're all bounded in a way. So then, and we also require like the volume form is also bounded. So, and or covariant derivatives this volume form and its inverse are bounded. So roughly speaking, this metric that doesn't blow up at infinity, and this volume form is controlled as well when you go to infinity. And let's just call this one a bounded Calabi-Yau geometry. Which one?
Kähler.
Complete, yeah. I require Kähler, yes. Now, the second notion I need is the following. Toward this Hodge-to-Drum degeneration, I need some growth control on the superpotential when you go to infinity. So in this case, suppose this pair is bounded, so like all this metric and this derivatives and curvatures are bounded. Then this map, this superpotential, this F, we call this one strongly elliptic. There are different notions, or this how strong it is, and the statementless conditions. But I'm gonna use the precise one. I'm gonna use is the following. So take any epsilon bigger than 0, k bigger or equal to 2, and this guy minus goes to infinity as they go to the boundary. So it means like this multi-derivative of this superpotential like goes to infinity much smaller than this object for any kind of order for any epsilon. So this one goes to infinity much faster than this guy, controlled by this object. So roughly speaking, it's like all higher derivatives of the superpotential is controlled by the first order derivative. And that's roughly speaking the data. It looks a little bit strange, but this is very natural if you try to study this harmonic analysis for this.
And F has a critical point at infinity.
This doesn't work for. In our case, we can only deal with like compact supported. I don't know what's happening for that. I mean, at least we don't have a control. Because at some point you want to. The question is like.
Can X be C2 minus a point?
Yeah, that's no problem. Yeah.
But then
The point cannot. Yeah.
That cannot be critical point.
Yeah. Exactly. So let me just tell you a bunch of examples which falls into this setup. First one, like it's a mirror for this FJW theory, and basically this pairing is standard volume form on Cn, and G is the standard flat metric. And F is the non-degenerate. Quasi-homogeneous polynomial. This is the model which deals with like the mirror of FJW theory. And this is one example. And actually, we now know the full mirror theorem for this one. Like, just let me write it down. The mirror theorem holds. In this case, it's like in this work. Basically, the place we do this process and calculate the corresponding information manifold, and you can find it's equivalent to this mirror FJW theory. And the second class is like probably you are more somehow like it. It's the mirror of the toric. And G, again, is a standard metric, complete metric. And the superpotential on this one is somehow so-called convenient. Non-degenerate. Lorentz polynomial. This is for the mirror of toric. And this means like the zero lies in the interior of the Newton polytope of the superpotential. So once this one is satisfied, you can show this is one example of this strong elliptic case. And the third one I want to mention it's a Landau Ginzburg orbifold. So it's supposed like this is like a Krapman resolution. And G is a finite subgroup f of SUN, finite. And then my omega is a standard volume form downstairs. This was invariant. And you can write down the metric. The metric is like asymptotic locally Euclidean metric. G is ALE. And this is the model for orbifold. Landau Ginzburg B model. Basically, you can. By the way, you need some. This guy is a polynomial which is G invariant. So it leads to a superpotential. Leads to superpotential here. And this superpotential, this pairing, is basically the model like that. And because this is Krapman resolution, the downstairs, like orbifold Landau Ginzburg model, somehow in the B side is equivalent to this model because this Krapman resolution basically modified the Kähler class a little bit. And the B model is insensitive to Kähler class. But it's not the same if you work on A side. So on the A side, you will need a bunch of like wall crossing process.
So if you start with X being possible projections, and then everything is algebraic, are all these conditions automatically satisfied?
Not automatic, I have to check.
So there's no critical point infinity.
I'm not sure how general is that, actually. Because this is not completely trivial for this condition. But
It's not clear how you use it for
yeah. Yeah, I don't know. I mean, it's not clear at this moment to me. Yeah, but this is not the strongest. This is not the full. I mean, this condition can be weakened for sure. Like we haven't done this one in the most refined way, but somehow.
If you have no critical point in infinity, and things are algebraic, how can that fail?
Yeah, that's how basically how you prove this. For example, how you prove this case, is just as you said. How can you fail? You just write it down. Yeah. But I don't have a theorem for that. Yeah. Okay. So all these examples, like 1, 2, 3, are examples satisfying this strong elliptic condition. So let me now write down the theorem. It's a theorem with Wenhao. So suppose this guy is a bounded Calabi-Yau. And we have a superpotential, which is a holomorph function with compact support, a compact critical point. Yeah, sorry, compact critical point, and strong elliptic. The statement is the following. Then first, the complex wrote down, for example, this object. This complex, did I erase that? This complex is a complex where where is the? Oh yes, this space. Yeah, this space with this twisted D-bar operator and this divergence operator. This is like DG-BV algebra. This one is a DG-BV algebra with a pairing. Basically, the trace is well defined on this one. Integration is convergent, and you can show using this model, this Hodge to drum degeneration holds. Second, and this model basically is quasi-isomorphic to both models we just described. So we have actually a subcomplexes it turns out this one, every element here is represented by smooth functions, and then this lies in between. And these are all quasi-isomorphic. Quasi-iso. And in particular, this is quasi-isomorphic embeddings. In particular, since this Hodge-Durham degeneration holds for this complex, it also holds for this guy and holds for this guy. So this implies that, in particular, this Hodge-Durham degeneration holds for both models, let's say the last one. Because this last one is the one we can relate to algebraic models, like the resolutions of by holomorphic functions or algebraic functions. So somehow this explains, like, if you just forget about this technical issue, just work with this complex or black complex, you do the standard construction. In this case, it still works. And the last one I want to tell you, like, this is Poincare duality still holds. This is the one you write down this pairing, and you invert this pairing. You write down this, for example, the J functions and things like that. The trace map.
This is the simplest example. Let's say if you look at C star, x being C star, x being C star, the function is Z squared. It's Hodge-Durham degeneration.
Which one?
C star.
Let me finish this one. Yeah. So yeah, we can discuss in the break. Yeah. So yeah, it's a little bit. So this trace pairing on the cohomology. It's non-degenerate. And then this implies also that this is a generalization of QG-Saito's higher residue pairing.
This topic you don't need strong relationship.
Oh, this one is let me see. You need this L2. You need this L2 space to write. Yeah. That's right. Yeah, you only need L2. That's right. Yeah. And so, by the way, I'm presenting this analytic construction, but just probably final remark is the following: like, there's algebraic versions of this Hodge-Durham degeneration. A lot of works along this line. It's algebraic approach. Most of the algebraic approach basically is based on this characteristic P method. And let me just mention a bunch of people. It's not all, but some major works are done there. Sabat and August Wolowski. And also, you know, this work of that's not Sabat and Yu Zhendao. In different setup, like or some other also works for irregular case and things like that in the algebraic setting. Kazakov, this famous KKT paper. Kazevich, Panchov. Yeah, if you like more algebraic setting, you can look at these papers. For Hodge-Durham degeneration, basically once you have this one, like 1, 2, 3, and this implies that a Formalist manifold structure holds can be constructed on on the comargin. Yeah, so actually I'm running out of time, so let me stop here. We can discuss along the, yeah.